All right, we're going to continue our discussion about functions and their properties involving continuity properties and more. Okay, so on your guided notes here, I want you to notice that I have three places or three types of discontinuities a function might have. Okay, and the first one is a removable discontinuity, and a removable discontinuity looks like what I have right here. So we're at x equals a. It looks as though my function looks really nice going from left to right until I get to a, and I have a break in my domain here, and then I continue on after x equals a. And so my function is continuous everywhere here except at x equals a. And they call this a removable discontinuity because it looks like I just removed a single point and threw it away. Okay, so that's a removable discontinuity. All right, and the one next to it is an infinite discontinuity, which is also a break in the domain. So if I'm moving from left to right, my function is increasing until I get to x equals a, and then I have to have a break in my domain and hop over x equals a, and then I continue my function. So this is an infinite discontinuity. Now what makes it different than this one is I took out more than one point. I took out infinitely many points, and if I were to try to put them all back, it wouldn't be a function because that's a vertical line. Okay, and so the third type of discontinuity we're going to talk about today is a jump discontinuity, where if I go from left to right on my function's really happy, merrily going along until I get to x equals a, and all of a sudden it jumps down to this y value and then goes on. So it's continuous on the left side, and it's continuous on the right side from a to infinity, but not including a. All right, so what I'd like to do is talk about how the limits work here. Okay, so I'm going to say that, let's just say that this is 1 here, okay? And if I wanted to figure out what the limit was as x approaches a from the negative side, and we use a superscript here on the a, from the negative side, that means as x gets closer and closer to a, the y is getting closer and closer to 1. But from the left side, it's getting closer and closer to 1. Okay, and then the limit as x approaches a from the positive side, or the right side, as x gets closer and closer to a, my y is getting closer and closer to 1. And so what's nice about that is a removable discontinuity, the limit from the left equals the limit from the right here, but I have a break in my domain because I have an open dot here, right? So how would we write that? Well, we would say that the limit as x approaches a from the left of f of x is equal to the limit as x approaches a from the right of f of x, but it's not equal to f of a, meaning I don't have a dot plugging that hole. Okay, now these two discontinuities are called non-removable discontinuities, these two. And it's just because they're different, and that you took out multiple points versus just removing this one point, okay? So let's see how the limits work around x equals a for this infinite discontinuity. Well, the limit as x approaches a from the left side, or the negative side of f of x here, the limit as x gets closer and closer to a, my y is getting closer and closer to, from the left side, positive infinity. And the limit as x approaches a from the right side of f of x, in this case, as x gets closer and closer to a from the positive side or the right side, my function, my y value, is getting closer and closer to negative infinity. And what makes this different than this jump discontinuity is that an infinite discontinuity, the limits as you get closer and closer to A are infinite. Even the limits are infinite. Okay, so let's talk about the jump discontinuity and its limits as you get closer and closer to A. All right, so the limit as x approaches A from the left side of f of x for a jump discontinuity, we'll call this 1, and we'll call this -1 here, so we have some numbers, okay? The limit as x gets closer and closer to A from the negative side or the left side, the y is approaching what? It's approaching 1. All right, let's try the other direction. The limit as x approaches A from the positive side. So as x gets closer and closer to A from the positive side, the y is approaching -1. And do you see how these aren't equal? So the y values are essentially jumping from one finite number to another finite number. And we can say that the limit as x approaches A from the left side is not equal to the limit as x approaches A from the right side of f of x. Okay, so the limits don't meet because 1 is definitely not equal to -1. They jumped y values, okay? Now, there's a special case of a removable discontinuity I'd like to talk about, so I'm going to graph it really quickly here. Let's say we have a similar function, and I'm going to try to make it look similar. And I have an open dot at A like I have above there. Now that's removable, but you can also have a removable discontinuity where I have not at 1, I have a point, but let's say I have a point at 2. This is also removable because it looks like I removed the point, but it's still not equal to f of A. Do you see that? So I would have 1 equals 1 is not equal to 2 here because that one is 2 because your function value is 2. Well, after all of that, for continuity, what's different for a function to be continuous? Well, the limit from the left has to equal the limit from the right, so they have to meet up. But what has to be true for this to be continuous? They not only have to meet up, but f of A, which you would expect to find here, that's got to be a solid dot for it to be continuous. So let's draw that real quick. See the subtle difference here, well, it's not too subtle, I guess, is that the limit as x approaches A from the left and the right are the same number. They're both equal to 1, and now it's equal to f of A. So for continuity, the limit as x approaches A from the left of f of x has to equal the limit from the right as x approaches A from the positive side has to equal f of A. So they all have to be equal. So I have to be approaching from both sides the same limit, the same y value, and then the function has to have the y value that I'm approaching for it to be continuous. So this is the limits for continuity here, which is a big deal. Okay, now continuous functions, essentially are as simple as, when I drew this, I didn't pick my pen up off the paper. It was continuous throughout. Okay, all right, so that's property of functions is continuity. Another property is whether we can tell whether it's increasing or decreasing, and we did some of that in the last video here. So a function is increasing if you put your finger on your function moving left to right, and you should always move from left to right. Is your y value moving up? Is your y value getting bigger? Then your function is increasing. If you put your finger on the function and going from left to right, you go down, your function is decreasing. And if your finger doesn't move at all in the y direction, up or down, it's constant. Okay, now the key to all of these is that you have to, if I'm telling you your function's increasing, I'm telling you already what the y values are doing. So the biggest thing that folks miss is the x values. These, you gotta use x intervals. And I'll give you a quick example down here. Let's say we had one of our functions that we just talked about. Let's say we had f of x equals x squared. Okay, so here we go. That's our toolkit function. We'll talk more about in the next video here. Here's the toolkit function. But everybody knows what x squared looks like. And of course, it's not symmetric because I did it by hand, so you have to bear with me. But if I put my finger on the function moving left to right, well, it's clearly my y values are going down. Well, what x intervals are they going down? So I would say f of x is decreasing. And do you see how f of x is another way to say y is decreasing? Well, if you're telling me what y is doing, I want to know for what intervals. From negative infinity to 0. And when you go past 0, your y values are increasing. So you would say f of x is increasing from 0 to infinity. Now, I like to think about physics here, and I say at 0, it's neither increasing nor decreasing. So I use open intervals to describe my increasing and decreasing x intervals. Because which do you choose at x equals 0? Do you choose that it's increasing, or do you choose that it's decreasing? It's next to impossible, I think. We're remembering that these are x intervals. Why? Because I'm telling you what y is doing, right? And those are the x intervals where this is happening. All right, that's a bit of a review, I hope. The next part is extrema. Now, extrema is a fancy word of saying maxes or mins. Maximums, minimums. That's an M. Now we have two different types. We have local or relative maxes or mins, and then we have absolute or global maximums or mins, okay? Now I have a sketch here of a function, and we're going to discuss what these points are. Okay, well, at x equals a, I have a minimum because in the neighborhood here, that is the lowest y value. But is it the absolute lowest y value? Meaning, is it in this function, is there any other y value that's lower than that? And the answer is no. So that is an absolute minimum. All right, now I keep moseying along on this function at x equals b. In this neighborhood of b, that is the highest y value. So that is a relative maximum because there's a y value that's higher. Okay, so this is a relative maximum. And there's nothing here because I continue to be decreasing, right? Until I get to a relative minimum. And this is relative because that's a lower y value. And then I keep going, and at x equals d, I have an absolute, which is also a relative max. Now this is also a relative minimum. Because in the neighborhood here of this absolute minimum, is that the lowest in its local neighborhood? Yes, so they can, like this is the absolutes are also relative or local because in their local neighborhood, they are the lowest y value, okay? This one is clearly the absolute highest y value, so that's the absolute max. It's also in its neighborhood. Is it the highest y value? Yeah, so it's also a local. But when you're looking at the bigger picture, you would call that an absolute max because that's telling you even more information. And then E down here, if this is a solid dot here, this is a relative minimum because in its neighborhood, it is the lowest y value, but it's not the absolute lowest because that is the absolute lowest, okay? Hopefully that's a bit of a review, okay? And the extrema are the y values. Not the x's. The x's are where they occur. All right, so let's fill out this information here. Let's say I have this function, and I wish this had arrows on it, so draw them in. Okay, and we're going to assume, it says for this function, assume the domain is all real numbers, so it's going to go on forever. Okay, so we're going to answer the following questions. So the first one says the function is increasing. The function is increasing over, this should be over the intervals. Okay, so increasing, that means when I put my finger on the function moving left to right, my function is increasing from, what are the x intervals? From negative infinity to a, right? So I'll go from negative infinity to a. You notice I did not use b, I used the x intervals where my y's were getting bigger. And then from here, from 0 to x equals d, so we'll say from 0 to d. That's where I put my finger on the function moving left to right. My y values are getting bigger. Part B says, well, function is decreasing over what intervals? Well, increasing, increasing, decreasing from a to 0. And that's the only interval I see that it's decreasing. Part C says the function is constant over what intervals? Well, it looks like it's constant from d to infinity. And then the function has local maximums at what point? Well, I would say this has a local maximum at AB. Now that's the point, but how would I say it? I would say f of x has local max of b, that's the y value, at x equals a. All right, it also has an absolute maximum here. F of x has an absolute max of e over, it's got an interval now, and you're going to have to include d because d's value is e, d to infinity. Okay, so all the x's where that applies is from d to infinity, so that's a maximum, okay? Part E, the function has local minimums at 0c, so we would say f of x has local, or relative you could use, minimum of c at x equals 0. All right, now let's do the end behavior limit. So limit as x goes to negative infinity. That means I'm going down the x's. X gets closer and closer to negative infinity. The y is getting closer and closer to negative infinity. So this is negative infinity. The limit as x goes to positive infinity. Well, if I go to x positive goes to positive infinity, the y is going to, well, it's not only going there, it's there already. It's going to be e here. It's the end behavior limits. Okay? All righty. Moving along here. Now, if you struggle a little bit with the increasing, decreasing stuff, this is what I recommend that you do. This helps sometimes. On the bottom here, my function is increasing from negative infinity to, I get here, right? So it's increasing. And then what happens? It's decreasing till I get to here. And then it's increasing again to here. And then it's what afterwards? It's constant. And then you can see that it's the x intervals that we care about. So if that helps, that might help. All right. Let's do the next page. Let's do some end behavior limits of some common functions. Okay, so these have arrows on the end here. This is a line, y equals x. And the limit as x goes to positive infinity. If x goes to positive infinity, the y is going to positive infinity. The limit as x goes to negative infinity. As x goes to negative infinity, the y is going to negative infinity. All right, these have arrows on them too. So this is a parabola, y equals x squared. As x goes to positive infinity, the y is going to positive infinity. As x goes to negative infinity, the y is headed to, or f of x is headed to, positive infinity. This is a cubic. The limit as x goes to negative infinity is positive infinity. As x goes to positive infinity, the f of x is going to positive infinity. As x goes to negative infinity, the y is going to negative infinity. This is a classic quartic. Okay, this one's got negative end behavior. So the limit as x goes to positive infinity, the y is headed towards, the f of x is headed to negative infinity. The limit as x goes to negative infinity, as x goes this direction, the y is headed to, or the f of x is headed to negative infinity. All right, this is y equals 2 to the x. So as x goes to positive infinity, the y is headed towards infinity. The limit as x goes to negative infinity. As x goes to negative infinity, the y is headed towards, now this is an asymptote here. That's right, I heard it from the back, is 0. All right, now this one is y equals 2 to the negative x plus 1. So the limit as x goes, now this is an asymptote here, and these have arrows here. So the limit as x goes to positive infinity is 1. And as x goes to negative infinity, the y is approaching, or f of x is approaching infinity. All right? Good. So that's a quick review of end behavior limits using pictures of functions. All right? So now we're going to talk about where do we have issues? Well, we have issues on for continuity. If you recall, when we discussed continuity, you might have issues at piecewise functions. You can have piecewise functions where they might connect and have an open dot, or you can have a piecewise function where they not only meet up, but they connect and have a closed dot. So we're going to figure out what these functions are doing. Okay, so this says graph the function on your calculator and tell whether or not it has a point of discontinuity at x equals 0. But we're going to do it by hand because we're in pre-cal and we're pretty good at piecewise functions, right? So here we go. So I'm going to draw my XY chart here, and the break here is at 0. And I'm noticing here that these are both open dots. Now I like to do this so that I, refresh my memory so I know they're both open dots here at x equals 0. But so x plus 2 applies when x is greater than 0. So when x is 0, I get 2. So I'm going to hop up here and I have an open dot. And then my slope is 1, so I have a line that goes this direction with a positive slope. Okay, when x is less than 0, I have the line negative x plus 2. So when x is 0, I have 2, but this is open, and I have a negative slope, so I now have to go over 1 and up 1. So it's going to be like this. So what's going on here? That we wanted to graph our function and tell whether or not it has a point of discontinuity at x equals 0. Well, it does, and what is its type? Well, we would say that f of x has a removable discontinuity at x equals 0. Now, how would I write the limits for that? Well, that would be the limit as x approaches 0 from the left side of f of x. Well, that's equal to the limit as x approaches 0 from the right side, but it's not equal to f of 0, right? Because That's an open dot there. All right. So that's how we notice we have a removable, right? Because the limits say they meet up, but what happened when they met up? They didn't have a solid dot there. All right, let's do part B. Okay, I'm going to draw my little XY plane here. And now I know I have an open dot on this side and I have a solid dot on this side. So at 0, when I plug in 0, I have -1. And this line is has a slope of 2, and that's when x is greater than 0. So I'm going to go up 1, 2, and over 1. So my slope is pretty steep here, right? But this is an open dot when x is greater than 0. There we go. All right. Now this is going to be a solid dot on 0, but when I plug in 0, I get 0 minus 1, so it's -1. So what's happening is this one's going to fill the dot, and it has a slope of -2, so it's going to be over here. So what do we know about this one? Well, this one is continuous. So f of x is continuous because not only do they meet up, the solid dot is filled. So we're going to say f of x is continuous at x equals 0. And we can say since the limit as x approaches 0 from the left of f of x is equal to the limit as x approaches 0 from the right of f of x is equal to f of 0. Now, this one, the limits were equal to 2, but guess what? F of 0 did not exist. So that was the problem here. But what's the limit here as x approaches 0 from the left? My y value is approaching -1, and that's equal to -1 from the right side, and that's equal to f of 0. So all three of these are equal, so I am continuous. They meet up, and then they fill the hole. All right, let's try this next one. So they would connect or not connect at 0 here. So when I plug in 0, this is an open dot, and this is a solid dot. Okay, so let's see what happens. X squared minus 2 for x greater than 0. When I plug in 0, I get -2. And it's an open dot. And it's a parabola that's shifted down by 2, but I only want the right half. Okay? And then the bottom part, or the left side, is -x. Well, what happens when I plug in x equals 0? Well, that's 0, but that's a solid dot there because that's closed. And then I have a slope of -1, so I'm going to have a slope of -1 on this left side. And so what kind of discontinuity is that? Well, we can say f of x has a jump discontinuity at x equals 0 since the limit as x approaches 0 from the left of f of x is not equal to the limit as x approaches 0 from the right because the y values are different, right? So as x gets closer to 0 from the left side, I'm approaching 0, is definitely not equal to the limit as x gets closer to 0 from the right side is -2, right? It doesn't even matter that this is not solid because I'm not approaching the same number from the left and the right, so I can't be continuous there. All right, this next one has 3 different branches, so let's graph that. So less than -1. We know that this is open, and this is open, and then it's closed, and this one is open. All right, so when I'm graphing it from the left, when I plug in x equals -1, I get -1. So we'll put a -1 here, and that's an open dot at -1, and it's y equals x, so it has a positive slope, +1 slope. There it is on the left side. Okay, now let's do the middle part. Well, the middle part is x squared. Well, when I plug in -1 to x squared, I get -1 times -1, which is 1, and it's open. So this is 1. It's open, and then at 1, it's closed, and that's 1, because when I plug 1 in, I get that. So this is the parabola part in the middle. And this, I'm going to make this look more like a dot here. Okay, and now let's do greater than 1. Greater than 1. When I plug 1 in, I get -2 minus 4, which is, wow, holy cow, it's all the way down here, -6. And it's open. And I've got a -2 slope. Oops. It's not at 0, right? I'm going to put it down here so I can see it some. It's here, I'm sorry, it's at 1. And I got a -2 slope, which means I have a slope that looks like this, -2, and it goes down. So what's going on this one? I have a jump on the left and I have a jump on the right here. So we're going to say f of x has jump discontinuities at x equals -1. And why is that? Because the limit as x approaches -1 from the left side is not equal to the limit as x approaches -1 from the right side. So what are those y values approaching? From the left side, I'm approaching -1 is not equal to 1. And at x equals 1, the limit as x approaches 1 from the left side is 1. And that's not equal to the limit as x approaches, whoops, let me put my f of x in here. Sorry about my notation there for a moment. X approaches 1 from the positive side is, oops, that's -6. -6, and they're certainly not equal, but they're finite values, so they're not infinite discontinuities. All right, really quickly, I want to show you how to graph these functions on your calculator. So let's go to the first one here. And if I go y equals, now, on the newer editions of the TI-84, if you hit math and you scroll down or scroll up, I'm going to scroll up. Do you notice that I scrolled up and I see that this has piecewise here? So I hit the math button, and instead of scrolling down, I scrolled up to get to piecewise faster. So it's going to be piecewise, and when I press enter, how many pieces do I have in this one? I have 2 pieces, so I'm going to type in the number 2, or you use the right or left arrow, and I went down to 2 pieces, and I'm going to press OK, and it shows me my 2 pieces here. I'm going to zoom in a little bit here so you can see it better. Okay. Now, what are my 2 pieces? Well, I have x plus 2, and then I have to do the condition, which is x. Now, to get to the greater than, you have to hit second test. Second test. And that gives you the logic conditions. I'll make it less blurry here. So the logic condition is greater than. So I'm going to choose number 3, 0. Okay, I'm going to hop down to my next branch, which is negative x plus 2. And then I'm going to type in x less than 0. So we get to the less than by hitting second test number 5, 0. Press enter, and I'm going to hit graph now. I'm going to do a zoom 6 actually. Here we go, zoom 6. And I want you to notice that it's very difficult to see whether that's open or closed. Okay, so we have to use our head and say, well, they're both open, right? So if they connect, that has to be an open dot. Now there's one place you can see it if you look at the table. So I'm going to go second table set. I'm going to start my table at 0, and I'm going to get close to 0. Okay, so I'm going to go second table now, and you'll see that I have an error, don't I, at x equals 0, which means that's an open dot there. And you can see the limit as x gets closer to 0, that your y's are getting closer and closer to 2. So they're getting closer to the same number, which is pretty cool. All right, so I'm going to do the one on this calculator with the 3 branches because that's different, if that's all right. So I'm going to go y equals, and I'm going to deselect this one by hitting the equals and hopping off. And then I'm going to put it in y2, okay? So how do I get to the piecewise command? Well, you hit math, and instead of going down, you're going to go up to piecewise, press enter, and this one has 3 pieces, so we're in business. So I'm going to type OK, and now I have my 3 pieces. So we're going to type in X, and now we have to put the conditional in, and we're going to say X less than, and you get to the conditional going second test, and we want the less than, which is number 5, -1, and then let's go to the second branch, which is x squared, and we're going to go to the conditional, which is -1, second test, less than, which is number 5, x less than or equal, so second test less than or equal to, which is going to be number 6, and then we're going to type in 1. Okay, and then we're going to go to the last branch, which is 2x, last piece of the branch, -2x minus 4. And I'm going to hop to the condition, which is x is greater than 1. So we're going to go second test, greater than is 3, and then we're going to put 1 here, press enter, and then we're going to graph it. So there it is. There's this first piece, and there's my parabola, and then there's my second piece, my third piece over here. Now, please notice that you don't see that this is an open dot here and an open dot here. It's really, you can't see that on the calculator. So you got to be very careful. Okay. But who knows that they're open? Well, you do, because you are being cognizant of the fact that there's no equals here. No equals here, but there is an equals here. Okay. All right. So that's how you do that. Now, if you have an older calculator, I'll have to do a video on how you do the piecewise with an older calculator, okay? Now, the last part of this that we're going to do before I end our video here today. No, actually, I'm going to do more practice with domain. But what we're going to do is we're going to graph these on our functions on our calculator, and do the domain and range, okay? But there's some of these that we can do the domain and range without our calculator. So this is a cubic function that's negative. So its end behavior with a negative cubic is going to be like this, if you recall, right? So its domain for a cubic is going to be all real numbers. Its range is going to be all real numbers. And the maxes and mins we're going to have to look on the calculator for, and the increasing and decreasing intervals. But we can do the end behavior limits on this because we know what it's doing. As x goes to positive infinity, this one's going negative infinity. And then x goes to negative infinity, it's going to positive infinity. All right, and now we're going to have to do some work on the calculator. So I'm going to go to y equals. I'm going to clear out my piecewise, all that hard work. And then we're going to type in negative x to the third plus 4x. And let's see if I can focus it a little bit better. Okay, and then I'm going to do a zoom 6 and see if I can see, that's the standard viewing window, if I can see any of the maxes or mins. Well, look at that. I can see the maxes. So the max is over here. So how do I get to a max? I want to know the point there. So I'm going to go second, calculate the maximum, which is number 4. And on the left bound, I'm going to hop over. That's the left bound of my maximum. And this is my right bound. Press enter. And I have the calculator guess, okay? And so my maximum is what? We can say we have a relative max of what? What's that y value? The y value is 3.08. 3.08 at x equals 1.15. Okay, and now how do I find the relative min? Well, we're going to go second, calculate the relative min, and now we're going to do our left bound. There's the left bound, and then we're going to choose a right bound and press enter, have the calculator guess, and the minimum is going to be at negative 1.15, and it's negative 3.8. So we're going to say relative min of negative 3.08 at x equals negative 1.15. And now I know these points, I can say what the increasing intervals are. Well, it's decreasing from x equals negative infinity until I get to this x value, which is, so I'm going to say decreasing from negative infinity to negative 1.15. And then it's increasing from negative 1.15 to positive. So negative 1.15 in the x direction, right? To positive 1.15. And then what happens after x equals 1.15? My function starts decreasing again. So this would be 1.15 to infinity. Okay, please note these are x intervals. That's a big deal. All right, let's do the next one. Y equals. All right, so let's type that in. I'm going to clear this out. This is negative x times second square root of 9 minus x to the second. I'm going to do zoom 6, zoom standard. Now, this is very interesting here because it looks like it doesn't reach. But I'm going to graph this on Desmos for you really quickly because I happen to have that window open. So we're going to say y equals x times square root of 9 minus x squared. Now, I want you to notice the difference in this picture and the one on our calculator here. What do you notice? Well, this one certainly goes to 0, and this one certainly goes to 0. But this one appears on your calculator to not go to 0. Well, and that's because your calculator doesn't have the ability to draw all the points that go down to 0 here. Because we're not looking at a 40 pixel television, sharp vision or whatever. But now, how do I know when I'm looking at my calculator that the domain is negative 3 to 3? Well, this is how you know. Does this have a square root? Does this have a domain gotcha? It surely does. We would know that 9 minus x squared has to be greater than or equal to 0, right? So that's 3 plus x times 3 minus x has to be greater than or equal to 0. And I do my sign chart. Ooh, we're going back to sign charts. My sign chart, and I'm going to put negative 3 on it, and 3, and that's a 0 and a 0. And if I superimpose the graph of this 9x squared, that's a parabola that opens down, right? And its y values are negative, and then positive, and then negative. And I can only take the square root of what kind of numbers? Positive numbers, or 0. So the domain's going to be negative 3 to 3 inclusive, and then the range, because I can plug negative 3 in here, what happens when I get negative 3 in here, or positive 3? 9 minus 9 is 0. So I know that my range is going to be from this minimum to this maximum, and the possible y value. So how do I find that on the calculator? We're going to second calculate the minimum, and we're going to be the left side of the minimum and the right side of the minimum, and press enter, and the calculator is going to tell us it's at negative 4.5. So we're going to say the range is going to be negative 4.5, and when does that happen? I'm going to put the minimum down here. So this is an absolute, actually, min, which is also relative, right, of negative 4.5 at x equals 2.12. And then let's find the max. We're going to go to the max, and then we're going to go to the left side of the max, and then to the right side of the max, and press enter, and we get 4.5. So we have an absolute max of 4.5 at x equals negative 2.12. So my range is going to be negative 4.5 to 4.5, inclusive, because those are the extrema. The increasing intervals, well, it's increasing from negative 3 to negative 2.12, and from 2.12 to 3, and then it's decreasing in the middle interval there, which would be negative 2.12 to 2.12. And the end behavior limits, well, the limit as x goes to infinity. Does this function exist when x goes to positive infinity? The answer is no. So this is dne. And the limit as x goes to negative infinity, does this function exist? Nope. So it's dne. All right, let's do another one. Clear this out, and we're going to get y equals, and we're going to do a fraction. So alpha f1 gives me the fraction, which is x to the second minus x over x plus 1. All right, and let's go to the graph because it's already in the nice viewing window. That's interesting, and that's interesting. Now you notice that the domain is going to be, right? How do we figure out what the domain on this is? Well, this has got a denominator, so x plus 1 can't be 0. So x can't be negative 1. So if I were to do a sign chart or the number line, that's open, but x can be anything else. So the domain here is going to be negative infinity to negative 1 in union with negative 1 to infinity. And let's look at the range. Well, the range is going to have y values from negative infinity to this maximum. And then I'm going to hop a bunch of y values, and then I got to figure out what the minimum is there. So let's figure out what those numbers are. Second, calculate the maximum. So I need to be on the left side of the maximum here and to the right side of the maximum. Press enter, have the calculator guess. So that has a relative max of, what's the y value there? Is that negative 5.83? Negative 5.83 at x equals negative 2.41. Okay, let's find the minimum. So second, calculate the minimum, which is number 3. Hop over to the minimum side. I'm on the left side of it. Now we're going to go to the right side of it, and we're going to have the calculator guess. And so this one has a relative minimum of negative 0.17 at x equals 0.414, so 0.41. Okay, so now we can do the range. We can say it goes from negative infinity to what y value? Okay, it goes to the max, which is, so the range is going to be negative infinity to negative 2.4, I'm sorry, the y value is negative 5, to negative 5.83, and I have to use a bracket here because it does include that maximum in union with bracket negative 0.17 to infinity. And those are both inclusive. All right, now this function is increasing from negative infinity until I get to that maximum. So using the x values, we're going to go negative infinity until the x value here of the maximum, which is negative 2.41. And it's also increasing from this minimum to infinity. So that's going to be the x value of negative 0.17 to infinity. And then it's decreasing from this maximum, which is, oops, that maximum, which is at x equals negative 2.1, negative 2.41 to 1, to where's my asymptote? It's going to be at negative 1, and from negative 1 to that min, which is at negative 0.17. Now these are not points, right? These are x intervals. All right, so there you go. So that's how you use your calculator to find relative extrema, increasing, decreasing behaviors, maxes and mins, and how you use your calculator to help you out finding the domain and the range. But you have to be careful when you have square roots because the domain may look a little different than you expect. All right, well, thank you for listening, and we'll talk to you next time.